In this video, we are going to look at a special type of function called a contraction. Let's jump right into it. So here's the definition of what a contraction is. We have some function f defined on a metric space. And what's important here is that f sends the domain back into itself. So the codomain for f is a subset of the original domain. We say it's a contraction if there is some fixed number alpha between 0 and 1, but strictly less than 1. So that if we take any two inputs, plug them into f, and then measure the distance between their respective outputs, how far apart they are is less than or equal to this fixed number alpha times the original distance between the inputs. So it's like f can't stretch too much. And in fact, since alpha is less than 1, we think of f as kind of pulling points closer together. So it's a contraction. It's a well-named type of function. Let's start with this example. We'll see a few examples. Let's start with functions from R to R of the form f of x equals mx plus b. So the graph of this type of function is a straight line in R2. And we will say that the slope of this line is between 0 and 1. In fact, we could make it strictly between -1 and 1 if we wanted to, but we'll just make this assumption. We'll check this inequality. So what would it look like if I took two inputs, x and y, these are any real numbers, and plug them into this function? Well, we know exactly what that would do. It would be mx plus b minus my plus b. B's cancel out. The m here is between 0 and 1, so I could just pull it right in front and have m times x minus y. And at this point, we are done. Here, this slope m, I called it m to go with convention for lines, but this is what we want to think of as alpha. And as I mentioned, you could say the slope is strictly between -1 and 1, just so long as when you pull it out, you recognize that you would need the absolute value of m. Okay, so here's an example of a contraction. The distance between outputs is less than or equal to, here it's equal, but you could make it less than or equal to if you wanted to, is less than or equal to some fixed number alpha. So here this doesn't change for different inputs. It's fixed for the entire function times the original distance between the inputs, and alpha being between 0 and 1 is a contraction. So we're kind of shrinking distances closer to each other as we evaluate this function. Let's look at a few more examples. Next, let's look at the square root function. So I have two variations of studying the same function here. First, let's consider f of x equals the square root of x on this domain from 1 to infinity. So if you revisit the definition of the contraction, this is what we want to think of as m, our metric space. So it's kind of like ignore everything outside of the interval from 1 to infinity. The first thing you want to check is, does f send m to m? In other words, if I take the square root of any numbers between 1 and infinity, so greater than or equal to 1, do I land, say, to the left of 1? The answer is no. So it is the case that our function sends m to m. That's something that we need in order to say that we have a contraction. Okay, next let's just do that test. So imagine I took two inputs greater than or equal to 1 and plug them into the square root function. Okay, well that's just going to be square root of x minus square root of y. There we go, kind of struggling to order my thoughts. To handle this, what I'm going to do is multiply and divide by the same quantity, square root of x plus square root of y. The reason y is in the numerator, I will now have, this is like difference of squares, so if I expand this, or if I multiply these two terms together, we will end up with the absolute value of x minus y. And in the bottom, we have the square root of x plus the square root of y. But if you look back at the domain, both x and y are greater than or equal to 1. If I took both of these numbers and went down to 1, we'd be making the denominator smaller. If anything, that makes the fraction bigger. So this is less than or equal to the same expression, but replacing both of these terms in the bottom with square root of 1. So I would have 1 plus 1, that's a half, times the distance from x to y. This factor of 1/2 here works for any pair of inputs from the original domain. Therefore, we have a nice fixed expression here for alpha. And so yes, this first example is a contraction. We can say that if you take any two inputs from this domain, and plug them into the square root function, the distance between their outputs is less than or equal to 1/2 times the distance between the original inputs. Take a moment to experiment with the second example on this slide. So it's the same function, but here I've changed the domain. Now we're looking at inputs between 0 and 1. First check, does f send this interval back into itself? And then see if you can do something similar to this, or maybe you can't. So see how far you can take the second example. The first thing to check is that if you take any input between 0 and 1 and plug it into the square root function, do you go back to the interval between 0 and 1? And yes, you do. So this test is satisfied. Let's now imagine that we set up this computation, but I want to specifically choose one of the inputs to be 0 and the other one to be something bigger than 0. So let me imagine I have a non-zero input, and I'm going to measure the distance between f of x and f of 0. I'm going to choose this one to be 0. Same maneuvering as here. I can write this as 1 over the square root of x plus the square root of 0 times x minus 0, which I will go ahead and write out like that. And the issue here is that this number is unbounded as x gets smaller and smaller. So there is no alpha that is greater than or equal to 1 over the square root of x for all x in this interval. Let's see, what should I write here? But there does not exist a fixed alpha so that alpha is greater than or equal to 1 over the square root of x for all x in this domain. So, this, as x shrinks to 0, this blows up. So we are not going to be able to bound this expression above by some fixed number alpha. So this is not a contraction, right? So here we were able to show that the definition of a contraction was satisfied by finding alpha. And here I'm saying there cannot exist an alpha, because if you compare this to alpha times x minus 0, you can't say that this coefficient is less than or equal to alpha for all x that you could have chosen. The same alpha has to work. The difference between these two conclusions should make sense to you if you imagine the square root function. So if we plot the square root function over this domain, it's a very flat function, kind of like how our first example, when we looked at straight lines, it's like if the slope was pretty flat, it was a contraction. Here we have a pretty flat function over this domain. However, if we look at the square root function and include 0 in the domain, we know that, say, if you think about tangent lines, they turn vertical as we approach the origin. And compare, an input close to 0 with 0 and plug that into the square root function, if anything, we're stretching it very steep. So that steepness in our function around the origin illustrates why this example fails to be a contraction. These two examples also underscore the importance of thinking about the domain when you talk about contractions. So it's not enough to just say, oh, the square root function is a contraction, because that's not necessarily true. Anytime you are looking at a contraction map, don't just think about the function, also think about the domain. We need to perhaps recognize that functions behave differently on different types of domains. Also, don't forget this test. So always make sure that your function that you're analyzing sends the domain back to itself. This is a necessary condition when we're talking about contraction maps. Okay, let's look at 2 more functions before we move on to some results. Our next example is f of x equals the sine of x over 2 on the whole real number line. Okay, so since we have the whole number line as our domain, we know that f sends r back to r, so that's fine. What I want you to think about here is the mean value theorem. So let me first just set up any x and y from R. We know that sine of x minus sine of y, this is a difference of outputs. If you have a differentiable function and you're looking at a difference of outputs, which you are often when you're talking about contractions, always imagine to yourself what would happen if I took that difference in outputs and I divided it by a difference in inputs. Well, that would give me the slope of a secant line. the secant line segment passing through the points x sine of x and y sine of y, and the very famous mean value theorem tells us that this ratio is equal to the derivative of sine at some point c between x and y. Well, the derivative of sine we know is cosine. So this ratio is equal to cosine at some c between x and y. All right, that's really the key to this exercise. So take a moment to pause and now finish the argument to prove that this example is a contraction. Sticking with the same x, y, and c so that I don't need to reintroduce them in writing, let me then conclude that the distance between f of x and f of y, which, if I go ahead and factor that 1/2 out, is equal to 1/2 times the distance between sine of x and sine of y. Now I can actually solve for this absolute value in this expression up here so that this 1/2 times the distance between sine of x and sine of y can get replaced with 1/2 times the absolute value of cosine of c times x minus y, which I can write as the absolute value of the cosine of c times the absolute value of x minus y. I just dropped my marker cap, sorry. This expression right here is less than or equal to 1. So notice that c is going to vary for different inputs. This particular c relates to this particular pairing of x and y, but if I grab any two other inputs from R, it's very unlikely that it's going to be the exact same c. So there are infinitely many c's which would be appropriate in this statement, but what's true for all of them, so for any pair of inputs x and y you pick, is that this expression, the absolute value of cosine of c, is less than or equal to 1. So I can now write that this distance between f of x and f of y is less than or equal to 1/2 times 1 times the original distance between x and y. And that's what we want to see. So this denominator of a half here in this example is a little bit artificial, but you can think over why it was necessary. Also, go ahead and pause. Think about this final example that we look at before we start doing some proofs. This natural log example is actually a little bit of a trick, considering that we just talked about the mean value theorem. Because if you try to set up the mean value theorem for this example, it feels right at first. So if I write natural log of x minus natural log of y, again, the same kind of breakdown, we could say that for some c, some input between x and y, this would be equal to the absolute value of 1 over c, so the derivative of natural log at c times x minus y, and that feels promising. But if you haven't seen it yet, this is actually not a contraction. So if you concluded that it was because of this kind of statement, take a moment to realize what's going on in this example. So why am I telling you that this is actually not a contraction? What's failing here is that f does not send this domain back to itself. And that's because for all x greater than 0, natural log of x is under the identity function. So natural log of x is less than x, which means that natural log of, say, beta is less than beta. So it does not belong to this interval. And you can take a moment to think about how that tells us that we actually cannot turn this into a contraction on any kind of domain. So this is not going to work out for us. Let's now move on to proving that contractions are continuous functions. I wanted to take the broadest viewpoint that made sense in this moment. So what I put up here is the definition of a Lipschitz continuity. You can see that by just taking this number k and replacing it with alpha, a contraction is immediately an example of a Lipschitz continuous function. We're saying Lipschitz continuous, so let's prove that a Lipschitz continuous function is continuous, that adjective makes sense. And in fact, we'll prove something a little bit stronger. Every Lipschitz continuous function is uniformly continuous and therefore continuous. So that's actually what we're going to prove. The proof is very fast. So let epsilon be greater than 0 and choose any pair of endpoints x and y from the domain so that the distance between them, where I started to write absolute value, but here I'm thinking about a general metric space, the distance between them is less than epsilon divided by, I'm going to be careful here, it's tempting to write k, but technically k could be 0. You could do this in cases. The case k equals 0 seems like a very small thing to peel off, but there's a little trick here. Let's do k plus 1. That way, the denominator is always defined. So this choice works all the time. I'm omitting the language of delta here. Perhaps you would rather define delta this way and then choose x and y to be any pair of inputs from the domain which satisfies that the distance between them is less than delta. But let's just move on. Then we have that the distance between their outputs by the assumption that f makes this definition of Lipschitz continuity true, we can immediately say that this distance is less than or equal to k times the distance between the pair of inputs. But we know that that is strictly less than epsilon divided by k plus 1. And now you'll realize why this k plus 1 is a good choice. Not only does it make the denominator always defined, but this number is less than 1, right? So this is always like a good scalar to have out here in front of epsilon so that we can wrap up this computation. I haven't written too many words down here, but basically what we've shown is that for any pair of inputs, there's a delta. The same delta works for any pair of inputs so that when you evaluate the function on that any such chosen pair of inputs, the distance between f of x and f of y is strictly less than epsilon. So maybe I should add here, thus, f is uniformly continuous and so continuous. So Lipschitz continuity is automatically uniform continuity. Vice versa is not necessarily true. So being Lipschitz continuous is a stronger condition than being uniformly continuous, but that's stronger than plain old continuity. So a contraction is an example of a Lipschitz continuous function, which is therefore uniformly continuous, which is therefore continuous. Okay, now we're going to move into the contraction mapping principle, which is a really fun thing to look at. So we have a really fun proof to do. Here's the statement of the contraction mapping principle. Suppose that f is a contraction on a complete metric space. The adjective complete is important here, as you will see in the proof. Quick recap, what's a complete metric space? It's one where every Cauchy sequence converges to a limit that exists in the space. So if you compare convergent sequences and Cauchy sequences, in every metric space, a convergent sequence is Cauchy. But it's possible in some metric spaces to have Cauchy sequences which do not converge. And like, what would that look like? It feels like they're converging to something perhaps that doesn't exist in the space. However, if your metric space is complete, then that means that your Cauchy sequence will converge to a limit which exists and belongs to the metric space. Okay, so a complete metric space is one where Cauchy sequences converge. If we have this, a nice continuous function over a complete metric space, like the whole real number line, for example, then the contraction mapping principle tells us that there is a unique fixed point for the function. So a fixed point is an input which gets sent back to itself. So that's part of the statement, but the part of the statement that I think is really fun is that there's a way for you to estimate C. So it's like, how would you know where to look? And what you can do is grab any input from the metric space. So grab some x1. It could be anything. You don't have to make a good guess. So just pick anything, okay? Plug it into f. That forms a new point, possibly. So x1 gets sent to some next point, x2. Plug that back into f, plug that back into f. Just keep iterating this procedure of plugging your most recent output back into your function. You generate a sequence. And that sequence does not bounce all over the place. In fact, it converges to C. And I just think that's really cool. Let me give you an example. We did sine of x over 2 earlier. The fixed point for that is 0. So that's not very fun. But cosine of x over 2 is also a contraction. on R, this is going to be a contraction with the exact same argument using the mean value theorem as we saw with sine of x over 2. And if we want to find its fixed point, then we are looking for a number c from R so that f of c equals c. In other words, c equals cosine of c over 2. Or 2c equals cosine of c. If you graphed the line y equals 2x and y equals cosine of x, you're looking for that intersection point. This is much harder to solve than c equals sine of c over 2, for which the answer is 0. But here's how you could numerically approximate the answer. Pick any starting seed for this kind of recursive procedure that you like. Form the sequence. Okay, so what would be a nice seed to pick? How about 0? Plug 0 into f. F of 0 is cosine of 0 over 2, which we know is 1/2. And now plug that back into f. So 0, f of 0, f of 0, or in other words, f of 1/2 is cosine of 1/2 over 2. And then you could do that again. So I'm going to write cosine of 1/2. Sorry about my terrible handwriting right here, over 2. And at this point, I think you've pretty much got it to a couple decimal places. So the answer is approximately 0.45. Obviously, it doesn't terminate right after that 5. So try that. I think it's a really nice thing. So pick a couple contractions and take any starting point you like. It's fun that you don't have to make a good guess. It's not like Newton's method or something where you have to pick a good seed. Pick any point you like, one perhaps which is very far away from where you think the fixed point is. Start with that seed, plug it into the function, plug the result back into the function, keep plugging it back into the function, keep composing f with itself, and you'll notice that you converge on a point, which if you evaluate cosine of 0.45 over 2, it's approximately 0.45 because this is approximately the value of the fixed point for this function. Okay, we are going to prove this entire statement, and we're going to do it in a few different steps. So let me lay out those steps for you before we proceed. That second part of the contraction mapping principle, it's not just cool, but it also tells us how to prove the theorem because it gives us a constructive way to actually get to the fixed point. So that process that I went through with cosine of x over 2, we are essentially going to do that now in a proof. So here's kind of an outline of what we will do. Just a quick remark, because we have to keep successively applying f, we're going to be composing f with itself any number of times. Let's adopt the convention here that if I write what looks like f squared, it's not multiplication, it's composition. So f composed with itself, we'll denote that as f squared. That's f of f, not f times f. So that the first statement we can write concisely as saying that the distance between f composed with itself n plus 1 times and f composed with itself n times, that distance is something that we can understand. In fact, it's less than or equal to the scaling factor alpha to the n times the distance between the seed and just f of the seed. This tells us that we have a good handle on adjacent terms in the sequence that we form. Right, so we're going to pick any seed we like and we'll just keep applying f to it. So this part tells us adjacent terms can be described. We have a sense of how close adjacent terms in the sequence are to each other. And in fact, they are so close to each other that we can actually use the adjacency to kind of extrapolate into a Cauchy sequence. So from side-by-side terms to any pair of terms beyond some threshold, we will get that this sequence that we construct by continuing to iterate application of our function, it's a Cauchy sequence because our metric space is complete, therefore it has a limit. And that's how we identify the fixed point. We have to say, here's the fixed point. We have to describe it somehow, and we describe it as the limit of the sequence that we form. The ending is actually pretty fast. So the beginning is kind of technical. We just have to go through some estimates. And then we'll say, we know there's a limit. It's pretty quick to prove that the limit is in fact a fixed point and also that it's unique. That falls right out of the definition of a contraction. Okay, let me step aside so that you can read through this. Think about the steps. So again, adjacent terms, Cauchy sequence in general, the limit exists. That's going to be our fixed point, which we will prove is unique. I want to present this as a nice formally written proof. So here is the beginning of the proof, including with PF opening us up. Suppose that F is a contraction on some metric space M with scaling constant alpha. By the way, if I haven't said it yet, that number alpha, you can call it a Lipschitz constant since these functions are Lipschitz continuous. Now, choose any starting point from the metric space. Again, your first seed, what we call x1, which will kind of launch the sequence that we're going to form by continually applying f to itself over and over and over. That seed does not matter at all, so just pick some point from the metric space and form the sequence that we're going to analyze. Okay, so this is like a formal write-up for the proof. Now we're going to show this statement about adjacent terms in the sequence that we create. What we're going to do here is a proof by induction. So this statement is a statement on natural numbers. So for any fixed natural number n, meaning take any natural number you like, you can say this is true. That's a natural context for induction. So that's what we're going to do. Let me step aside just for a moment though, A, because you might be writing this down, so it's a nice place to pause, and B, now that I've told you to use induction, see if you can actually prove this with induction, and I'll come back and do it. All right, let's verify this claim. So by induction, add that to the proof. Notice when n equals 1, we have that the distance between, here we have 1 plus 1. So what I'm going to write as f squared is, of course, f composed with itself. So f of x1. Okay. Again, that's the last time I'll mention this notational convention that we are adopting here. So f of x1 compared with f of x1, what can we say about this distance? Well, f is a contraction, and these are two outputs. So we can say that this is less than or equal to the Lipschitz constant alpha times d of, just peel off one iteration of f here. For the first term, we'll have f of x1, and for the next one, we'll have x1, and that's it. Notice in the statement, that looks like prime, but it was supposed to be the number 1. So we're going to have alpha to the 1 power here. And I've just made everything look kind of bad, but all I wanted to say was that alpha equals alpha to the first power. Proceeding with induction, let's suppose that the desired equality is true for some k. Now suppose for some random unspecified natural number k, we know that the distance between the k plus 1th version, so f composed with itself k plus 1 times, and f composed with itself k times, we are making the hypothesis step here for induction. So we are supposing that for this particular index from the natural numbers, this distance satisfies the inequality. So it's less than or equal to alpha to the k times the distance between the second term and the first term. Consequently, I think this marker needs to be replaced. Okay, so consequently, we go up to the k plus 1th term, the next term, d of f of k plus 1 plus 1. And f of k plus 1, sorry, I'd say f of k plus 1, I mean composed with itself k plus 1 times. There we go. So the distance between these two terms, I'm not immediately going to apply the hypothesis. Instead, I'm first just going to recognize again that we're working with a contraction. These are outputs. We can go ahead and say, just peel off f once. It's alpha times the distance between f of k plus 1 again. F of k plus 1, I mean f composed with itself k plus 1 times and k times. Okay, let me hesitate here. So from the inductive hypothesis, we go to the inductive step. So I need to bump these up by 1, but these are outputs. So this inequality here has nothing to do with the induction. This is actually just verify, like this is just using the fact that f is a contraction. But now here, what we're left with is exactly what we had up here in the inductive hypothesis. So I can just immediately jump to replacing this with this and going up in size. So alpha times alpha to the k is alpha to the k plus 1 times the distance between the second term and the first. And that's what we wanted to show, so let me stop the induction there. Okay, so any pairwise terms are going to satisfy the desired inequality. If you're wondering if induction was strictly necessary, no, you could basically start with this and keep peeling off like a copy of alpha until you get all the way down to the second and the first term. So you could basically start with this and just say, hey, that's a contraction, just kind of undo all these applications of F, peeling out like an alpha each time until you get to this. So it doesn't have to be done with this kind of formal induction. You can get from this to this statement by just, again, recognizing it as iterative compositions of a contraction. But I wanted to bring in a proof by induction, so here we are. Okay, now that we know how to estimate the distance between adjacent terms in this sequence that we form, let's see if we can take these adjacent comparisons and make like a Cauchy style comparison between terms. I started to step away and I just thought, this is the second proof I've done this lecture where I haven't fully wrapped it up, so let me write as desired. Okay, now we are formally done with this first step. We'll move into the second one in just a moment. Now we will use the statement that we just proved in step 1 to prove this statement, that the sequence we get by successively applying F to the most recent output is a Cauchy sequence. This is going to be a nice proof that the sequence is Cauchy, so it will be a proof where we begin with let epsilon be greater than 0. Next, I'm going to choose some fixed threshold capital N, and here's how we'll do that. Since this Lipschitz constant alpha is between 0 and 1 and strictly less than 1, the sequence alpha to the n goes to 0. So alpha squared, alpha cubed. That's something we prove in the basic study of sequences. Thus, if I take this term here and just multiply it by a fixed number, that will also go to 0. So alpha to the n times just the fixed number, which looks like the distance between the second term in the sequence and the original seed, divided by 1 minus alpha. This is never 0 because alpha is strictly less than 1. This is a fixed number. This doesn't change with respect to this index n. So this going to 0 times this fixed number also goes to 0. Therefore, what we're going to do in this proof, and here you can tell I've already done the scrap work, but you'll see how you would have gotten to this if you started doing the scrap work in just a moment. What we're going to do is pick a threshold capital N so that for any index beyond it, this expression is smaller than epsilon. Okay, so choose some index capital N, our threshold for this Cauchy proof, so that for all little n greater than or equal to the threshold, this is true. Sorry, not this is true, but strictly less than epsilon. Right, so the sequence goes to 0, which means that for large enough indices n, I can say that this quantity is less than epsilon. Everything here is positive, no need for absolute values. Okay, that's how we pick the threshold. Now we need to do this kind of Cauchy comparison. So choose 2 indices beyond the threshold. Choose any, how I like to order this with Cauchy sequences is little m greater than little n greater than or equal to this fixed threshold. And notice we're going to do a triangle inequality argument. That the distance, there's this little thing here where the nth term is n minus 1 applications. Let's just, for convenience, write f composed with itself m times the distance from that to f composed with itself n times. This is the distance I want to not only understand but show is smaller than epsilon. Okay, this is a metric. We can do the triangle inequality. To compare this term to this term, I could go through the n minus 1th term, and then we just basically keep doing that to step from m down to n. So this distance is less than or equal to a bunch of side-by-side distances. So the distance from m applications of f to m minus 1 applications. Okay, so bring that in and basically just break this on up in a step-by-step way. Until we get down to n plus 1 applications compared with n applications. Okay, let me pause here. What I did was I let epsilon be greater than 0 because we're going to prove a sequence is Cauchy. And then in order to prove it's Cauchy, I need to identify some threshold. I did that in a way which might seem mysterious right now, but this rationale will come out in just a moment. Here's the heart of our Cauchy proof. I want to take any two sequence terms beyond the threshold, not necessarily side by side. In fact, we want to imagine that they could be very far apart. What can we say about the distance between these two kind of randomly chosen sequence terms beyond the threshold? Using the triangle inequality, I took this comparison and broke it up through a bunch of intermediary comparisons. So basically step down from m to n through adjacent terms, from m to m minus 1, n minus 1 to n minus 2, all the way down to n plus 1 to n. So that's repeatedly applying the triangle inequality to this. Now we have a bunch of side-by-side distances, and for this we're going to bring in what we just proved in step number 1 in this proof. So let me pause here, as it's a nice place to pause. Think about what we've written. I'll get out of the way so that you can actually read everything at once and see if you can anticipate what the next line is going to be. What we have here are a bunch of terms that look exactly like the statement that we just proved in step number 1. So let's bring that in. This term, I can say that this distance here is less than or equal to alpha to the n minus 1, so it matches this expression up here, alpha to the n minus 1 times the distance between the second and first terms. I'm going to just write this for now, because if I came here, I would say, and this distance is less than or equal to alpha to the n minus 2 times the same distance between the second and first terms. So instead of writing that distance multiple times, let me imagine kind of factoring it out to the right. So we'll have alpha to the n minus 1 plus alpha to the n minus 2 plus all the way down through alpha to the, how about n plus 1 and then n. So this one goes with the term here that I omitted, alpha n, all of these times the same distance. Like that. What does this look like? This addition here should look like a very famous type of series. Let me pause for a second if you didn't see that. So this should remind you of like a named type of series that we know. We can analyze it, and actually we can even add it up. So identify the relevant series here, and that will allow us to finish the proof. This looks like part of a geometric series. It's not the whole series, but it's part of the addition that you would do if you did the geometric series alpha to the n. Alpha, the base of our geometric series, we know is between 0 and 1, so it's a convergent geometric series. What I'm going to do is say that this part of the geometric series is less than or equal to, if I took alpha to the n plus alpha to the n plus 1 plus all the way through alpha to the n minus 1, and I actually kept going to do the infinite tail of the geometric series. So this is less than or equal to the whole geometric series, starting with n. So let me index with j equals 1 through, j equals n, that's important. J equals n through infinity, alpha to the j, times this. Okay. I'm almost out of room, but we have here an infinite geometric series that starts with alpha to the n, goes all the way out to infinity, so it includes all of these terms and actually more, infinitely many more, times the same number that they all have in common. This geometric series adds up because we know it converges. Alpha is between 0 and 1, less than 1. So it adds up to alpha to the n divided by 1 minus alpha. Here's the sum. So how do you remember that, right? It's a geometric series. The sum is something that you should know. If it converges, it's always first term divided by 1 minus the base. So first term here is alpha to the n divided by 1 minus alpha. That's the base. So alpha to the n divided by 1 minus alpha. That's the kind of scrap work I would have done on paper in order to arrive immediately at this estimate. We have chosen our threshold so that this term here times this constant number is less than epsilon. So I don't really want to erase everything, nor do I want to run out of room. Let me just keep going to the right. So this is actually going to be equality, my next step. This is equal to alpha to the n over 1 minus alpha times the distance between the second and first terms, which is exactly what we use to define the threshold. So this is less than epsilon. And imagine here I'm writing on the next line, as desired. Hence, the sequence is Cauchy. And that confirms the second step in this proof. This step is probably the most technical. The rest of the proof will actually be pretty fast. So do take a moment to work back through this. I would really encourage you at this point to, if you've written this down, kind of put it aside, get out a blank sheet of paper, and see if you can redo the first two steps of this proof. The reason why is because this proof is not random or strange. It's kind of a classic proof and analysis, meaning I wanted to compare two terms which are hard to compare directly to each other. So what do we do to do that? We brought in like intermediary comparisons that are much easier to understand through the triangle inequality. So using the triangle inequality, that's classic. And then we have this geometric series, and I want you to always recognize a geometric series when you see one. So that's why I think this is a good proof to kind of test yourself with. So put it aside or come back in 30 minutes or something like that and see if you could revisit this argument and if you understand all of the steps. Okay, let me step aside for a second now, and then we will move on to quickly wrapping up this proof by showing that now that we know we have a Cauchy sequence in a complete metric space, it converges to a limit, and it turns out the limit is going to be our unique fixed point. Because our metric space is complete, having a Cauchy sequence is equivalent to having a convergent sequence. So since our sequence that we've defined recursively is Cauchy, it's convergent, let C be the limit of this convergent sequence. I have a definition for C. I want to say that somehow that tells me f of C is also C. So what can I do with this? Well, imagine plugging both sides into f. So on the left, we would have f of C. On the right, we would be evaluating f on the sequence. Can we do that? The answer is yes, because f is continuous. Since f is continuous, we can use the sequential characterization for continuity. We have a convergent sequence in the domain. Xn goes to C. So f of xn goes to f of c. Let me swap the order here to write f of c on the left. F of c is the limit as n goes to infinity of f of xn, right? So xn goes to c, f of xn goes to f of c because f is continuous. Again, that's the sequential characterization for continuity. What is this? And for that, you might want to think about how we were defining the sequence terms. If I'm looking at the 50th term, and I do f of the 50th term, what is that? It's the 51st term in the sequence. So if you take your sequence terms and you apply f to them, you just shift one term down in the sequence. What you could do is take this expression and rewrite it as, say, x sub n plus 1. So whatever x sub n is, plug it into f, and you get sent to the next term in the sequence because that's exactly how we built up the sequence. But when we take the limit, what we're saying is, does this trend anywhere? And whether we're looking at xn, xn plus 1, it's the same sequence. It's trending to the same place. That place is now called C. And thus C is a fixed point. Okay, so So I think that's a nice short proof. Using the sequential continuity description, we can basically just plug that statement into F and we get f of c equals c. I said C is a fixed point. Turns out there's only one. Take a moment to pause and see what you would get if you tried to say that there was another fixed point. For that, think about the definition of the contraction F. It remains to show that a contraction, by definition, cannot have two fixed points. We can set this up as a formal contradiction. Suppose, how about D I'm using for the metric P? P not equal to C is also fixed by F. Then what I'm going to do is say the distance from P to C, P equals f of P, C equals f of C. So let's take these terms and just replace them using the fact that they are both fixed. Okay, so from here to here, I'm just using that they are both fixed points. Now looking at this, I'm going to use the fact that f is a contraction. I have the distance between two outputs. We know that that is less than or equal to alpha times the distance between the inputs. Alpha is less than 1. So I could actually just say that this is less than, strictly less than, what we said on the left, and that's not possible. Okay, so a number cannot be strictly less than itself. Therefore, there can be no other fixed point, so C is unique. And that wraps this up. I hope you enjoyed looking at contractions with me. And this contraction mapping principle, again, it's really fun. Here's an activity for you to do. Take any function that you know to be a contraction and find its fixed point doing that iterative procedure. If you haven't done a numerical algorithm before, if you're not comfortable with the idea of numerically estimating something, this is a really fun way to play with the ideas of it. So again, just take any function that you identify as a contraction, grab any point you like, maybe even one you think is far away from the fixed point, and just in a basic computer program or in your calculator, just repeatedly apply the function to whatever most recent output you've computed until you realize that you're converging on the fixed point. Okay, thank you for your attention.